This video will cover Unit 8 exponential functions. In this lesson, we will learn how to work with exponents, understand the characteristics of linear and exponential models, learn the key parts of graphing exponential functions, and then finally evaluate and solve exponential application problems. Our objectives are to construct and compare linear and exponential models, identify the characteristics of an exponential function, and then solve exponential equations by graphing. First, we will begin by working with exponents. Exponential notation is a shortcut for repeated multiplication. The exponent tells us how many times a number is used as a repeated factor. To write a number in exponential form, count how many times a number is being multiplied by itself, and then put that number as the exponent. It is common to use the letter B to represent that repeated factor, and it is called the base. Numbers in exponential form are also called powers of a number. So this is the fourth power of B. When working with exponents that have the same base, there are some rules or laws of exponents we can follow. So if we are multiplying two together, there's a rule called the product rule. And that just basically states that since the base is the same and the exponent is telling us how many times it's being used as a factor, if I'm multiplying two of those together, I might as well just add the exponents. It's much simpler. For dividing, we have a quotient rule, which is a similar idea. So since I'm going to cancel out m factors out of n, I'm just going to subtract them away. For power of a power, we have the power of a power rule, no special name there. And this is saying that b to the n is being used as a factor m times. Now I could keep doing this over and over and over, but since I'm doing this, that would be a number inside there. The shortcut here is to multiply those two exponents together. Before we go on to look at more laws for exponents, I think it's a good idea to stop and look at patterns as we work with exponents for the same base using descending powers. So I'm starting with 2 to the fourth power, or 2 to the fourth, and working all the way down with this same power all the way down, our base, down to 2 to the negative fourth. The first one I've written out, which I've expanded it out to have 2 times 2 times 2 times 2 equals 16. Now for the next one, there's a couple of ways I could do this. I could actually write this out in expanded form, which would then be 2 times 2 times 2 equals 8, or since I'm using one less power of 2, I could take this previous answer and get the same result by dividing by 2. And that's from our quotient rule. I've really got 2 to the fourth divided by a power of 2, and I still get that same answer, 8. So I'm going to use that quotient rule and divide each of my previous results by 2 to get my new result. So 8 divided by 2 equals 4. 4 divided by 2 equals 2, which makes sense. A base used one time should just equal itself. And then we have 2 divided by 2 equals 1. This is super important. A lot of people mistakenly believe that to the 0 exponent must mean times 0, and they'll put 0, but that is false. It does not. A base to the 0 always equals 1. Now we're going to continue with our pattern here. We have 1 divided by 2 equals 1/2. 1/2 divided by 2 is the same thing as multiplying it by 1/2, which would give me this because 1 times 1. So that's 1 to the 4th. To divide by 2, I can just keep doubling this denominator. By doing it this way, that gives me 1 over 8. And 1 over 8, double the denominator, gives me 1 over 16. Notice this answer here, 16 and 1 over 16. So this kind of gives us a little preview of this next rule. So this is the same thing as 1 over 2 to the 4th, 1 over 2 cubed, 1 over 2 squared, 1 over 2. So this negative exponent is basically telling us that our base is in the wrong part of a fraction and to put it in the correct part. So in this case, down to the bottom here in the denominator. So this gives us 2 more laws of exponents. So when I am working with negative exponents, I can move this around and write it as the reciprocal. So b to the opposite of n is the same thing as 1 over b to the n, and also 1 over b to the opposite of n is the same thing as b to the n. And 0 as an exponent, it does not matter what this base is. B to the 0 equals 1. And I am going to put a little star by that. There is disagreement whether 0 to the 0 equals 1 or whether 0 to the 0 is undefined. So which rule you pick on this kind of depends on your professor. There are some that say 0 to, or any base to 0 equals 1. Others say that this would result in dividing by a 0 at some point. Go with the rule that your professor tells you to go with on that one. For this section, we're going to talk about the characteristics of linear and exponential models. So we've talked about exponential models many times, and they are in the form of y equals mx plus b, and b is going to be that beginning value. M, the slope, is going to tell us how we're going to move on that. Exponential models, however, look like y equals a b to the x. So definitely they don't look the same here. Now, to really understand the idea of an exponential model, we're going to look at some characteristics of a linear and exponential model for 2 job offers. So Eric has just graduated from college. He has been offered 2 jobs. One is starting at $47,000 per year with a raise of $1,500 each year. The other one also starts at $47,000 per year, but is going to give him a 3% raise each year. For these, we're going to use year 0 as his first year, which is common when we work at models. We start at 0. And so if I look at this on after 1 year, or the first raise, 47,000 plus 1,500 is going to give me 48,500, the new salary after the first raise. For the exponential model, Eric would be making $48,410. What I would like you to do right now is to continue these tables. For the first one, you're just going to add a straight $1,500 raise each time. For the second table, you are going to add 3% of the previous year. Now you can use your calculator, make a table of values, or just however you wish to do those, but pause the video for a second. Then when you restart, we'll look at the answers. So that second year is 50,000 for this model. And I'm going to continue putting these values here because I could just add 1,500, 1,500, 1,500. So for the third year, we're up to 51,500. Now this table skips to year 5, which would be 54,500. And the 10th year, 62,000 a year, which isn't too bad here. Now for the exponential, we're starting lower. We started at the same time, but after the first one, 3% wasn't quite as much. The next race goes to 49,862. This is getting better. It's close, but still a little short. On year 3, we're at 51,358, which doesn't look like he's caught up. Oh, so close. But here, let's get to year 5, and now we're at 54,486. So at this point, a few dollars short, but almost the same. And at year 10, though, we're at 63,164. So he is making more at that point. Functions are of the form f of x equals a times b to the x, where the input x is located in the exponent. A is that initial value. If you've been given a function, you can actually calculate it by finding f of 0, which would give you a times b to the 0. Since b to the 0 equals 1, we have a times 1, or just a. B is that base. That base needs to be greater than 0, but it cannot equal 1. And that's because that base is a repeated factor. And if we have 1 times 1 times 1 times 1 times 1, we really are going to end up with a constant function, not an exponential model. So that B is also called the growth factor or the decay factor. And whether it is a growth or decay is dependent on that value. If b is greater than 1, this is an exponential growth function, and we can call that a growth factor. The graph will be increasing as we go from left to right. So we would see something that is growing or heading upward. If b, on the other hand, is less than 1 but greater than 0, so still positive, we have an exponential decay function, and we can talk about b as being the decay factor. That graph is going to decrease, so it's going to start up high and get smaller and smaller as we go on. So here we can see an exponential growth and an exponential decay functions here side by side, and there's a couple of key values that I would like to point out in this slide. So first of all, notice that when I am talking about exponential growth, it is growing. As I keep going, it gets bigger, it gets bigger, it gets bigger, it gets bigger, and it starts going up really high. And these are the ones for values where b is greater than 1. And this intercept right here happens at 0a, because f of 0 would give us that initial value, or a. For exponential decay, and I'll do this one in red for decay, b is going to be in between 0 and 1. It's still positive, but it is causing a function that is getting smaller and smaller and smaller and smaller. It also crosses, though, at the same spot at a. So our exponential functions, f of x equals a b to the x, either grows or decays at this constant rate. And that rate is a percent. We're going to call it r. So r is our growth rate or our decay rate in decimal form. So on a previous slide, we talked about a job offer with a 3% raise. In decimal form, that would be 0.03. So to find the growth factor, to be able to put that into a formula, we would take b equals 1 plus 0.03, or b equals 1.03. If we had an function and we knew b and we wanted to calculate the rate, well, we can do the same thing. That rate is going to be that b value, but this time working it backwards, subtracting the 1, and that would get us back to 0.03. Let's say instead, though, we had a decay factor. Let's say we have a function and it is decaying at a rate. Let's say the decay rate, we'll do this one in red so it kind of shows up, is 14%. Since we need r in a decimal, that's going to be 0.14. So this time we're going to find b, we need to subtract it because really a decay is a negative value. So really, I mean, that rate really is negative 0.14. So we have 1 minus 0.14 to find our b value. So b is going to be 0.86. If I wanted to go the other way, and I know b is 0.86, 1 minus 0.86 to find rate, and then that gets me back to that 0.14. So one of them I'm adding, one I am subtracting, but if you think of decay as being a negative rate, it almost works for adding both times. So now we have a table to fill in again. So do pause the video, and after you've done that, try, and done these things, then go ahead and restart and you will check your answers. So on here, the first one is f of x equals 812 times 0.71 to the x. So if I'm looking at this, this is definitely less than 1, so it is a decay here. So we're going to decay here. The initial value, the one outside of parentheses in this case, the growth or decay factor is that whole part. That's that b value, and that is 0.71. So our rate, though, is we need to find out what is the difference in there. So 1 minus 0.71, and so our r is going to be 0.29. As a percent, that is 29%. Okay. So for this next one, we're going to look inside here. What is our base? And our base is greater than 1, so that is a growth. Our initial value is 64.5. Our growth or decay factor is 1.32. Our rate is just 0.32 because I can subtract 1 out of there, or 32%. Now for these next two, we've been given a growth. Now we're supposed to find the the formula. Here's our initial value. You can use whatever you want. I'll just stick with the basic f of x. We'll start with our initial value. Now we need to know what is going to go inside these parentheses. And since it's a growth, I know it's 1 plus something. 1 plus something. And I can look at this rate down here. It says as a percent, it's 0.5%. So for 0.5%, I need 0.005. So 0.005. 1 plus that, 1.005. This next one is a decay. We have our initial value, f of x equals 150. Now this is going to be less than 1 inside that parenthesis. We have a decay of 20%. Again, that's as a decimal, that's 0.2. So I have 1 minus 0.2. I have 0.8 goes inside here. If you wish, you can put the 0. It's not necessary. So here's some additional practice. We've been given an initial value. We've been told whether it is a growth or decay and what that rate is. So pause the video, fill this table in, and then check your work. If you wish, you can kind of check them one at a time, but do pause and try this on your own. So for this first one, and I'm just going to use f of x for all of these. So f of x, and I'm going to take the initial value, 1500. It is a growth. So for all of the growth, it's just 1 plus that decimal version. So 1.15 to the x. The next one is a decay, so I'm going to go 1 minus that 0.15, so f of x equals 75, and that's going to be 0.85. If you wish, you could put a 0 in front, but don't bother if you don't want to. Next one, we have a growth again. Now this is a decimal, and sometimes people like to write it out and say, okay, yeah, that's 0.075. If you like to do that, sometimes it's helpful. So f of x, and that's 1250. That 1 plus that 7.5% to the x. Next one, we have a growth. This one also, it's still 1 plus that growth rate. It just happens to be 1.12 as a growth rate. So don't let that one mess you up. It is going to be f of x equals 12. 1 plus that is going to give me 2.12 to the x. This decay, so we're going to subtract out 1, whoops, forgot the equal sign, 1000, and that is 0.82 to the x. Decay rate of 5%, so I have f of x, 56.95 to the x. For this, if you wish, sometimes again, because of that decimal, we got 0% and then the 0.5. So very similar to the one up above, but with a little bit of a decimal shift here. We're going to have 0.995 to the x. And this one, again, if you also want to write out because of the funkiness with a decimal involved, sometimes it just helps. And this is going to be, here's our initial rate, and 0.938. So notice here, whenever you have that little decimal thing, you're going to get that 0.9, and then here's that 95 plus 5 gives it 100, kind of pops it over. 62 and 38 pops it over, if that helps you. So now we're going to look at graphing exponential functions. For your homework in more, it's going to be pretty straightforward, finding 2 points, and it will create that curve for you. And there are some points that are pretty straightforward to. As I look at the idea of graphing exponential functions, though, even though more is going to make it pretty easy for you, there are some key values or parts that you need to be aware of. So if I need to find a very easy point, we're going to look at that vertical intercept. And that's because remember that initial value of A is going to be my f of 0. Value does equal A. So my y-intercept or vertical intercept is at the point 0a. So I just need to look straight there. That horizontal intercept does not exist though, and we're going to look at those graphs again, and even though it gets really close to that line of y equals 0, it does not cross it. Our domain though is super easy, all real numbers, negative infinity to infinity, everything is fair game. Our range is f of x needs to be greater than 0. So in interval notation, that is from 0 but not including 0 all the way up to infinity. And this idea of horizontal intercept, that is because it didn't exist because we have something called an asymptote. And that asymptote is the line y equals 0, or our axis there. And that is kind of a funky concept to explain. So I'm going to show you some pictures here. So if I'm looking at asymptotes, an asymptote is a line that approaches a given curve or line but does not meet it at any finite distance, or in other words, it's kind of like a fence there. And exponential functions have what we call a horizontal asymptote. So if you're looking at the graph, you can see right here there's 3 general asymptotes that we think of. A vertical asymptote, this line here is getting closer and closer to that vertical boundary or fence, but it just doesn't land on it. Oblique asymptotes, over here, it's getting closer and closer. And then here in the case of our exponential function, we have a horizontal. This is a decay function. It's going down closer and closer to that line, but it just doesn't get there. So again, look at these exponential and growth and exponential decay functions. We've talked about them already, but you can see here now that even though this curve is getting close, it never ever crosses the axis here. So it's getting closer and closer, just doesn't go down into y is a negative value anywhere. And the same thing for the decay functions. It starts out really big, it's getting closer and closer and closer, but it just never reaches down to 0 there. So this is an example of graphing for more, and this is question 11 in your homework. So it says to graph the exponential function by plotting the vertical intercept and one other point, then write the vertical intercept as an ordered pair. So we can see on here that A, our initial value, is 5. So I can see that this is going to start right there. Not a problem. To get my second one, probably the easiest thing to do is to find f of 1. And so that's going to equal 5 times 3 to the first, or just 5 times 3. So when x is 1, we're going to go all the way up to here. And when you click, it will pop that curve in for you. So you're going to click the first point. When you get to the second one, it will automatically give you the curve. But those are the 2 points you're going to need. So for the next slide, so now for question 12, I would like you to pause the video, see if you can come up with the 2 points that you need, and then once you think you have them, go ahead and start the video and double check. So our 2 points, we do know that a value is 6. That's straight from there. So I have 0, 6. Now on this one, what I would like to do again is f of 1, because that gives me just 6 times 1/3. And 1/3 of 6 equals 2. So this is definitely a decay function. Again, when you click in, you will get that curve and it's going to go downward. But those would be the 2 points you need to get that graphed. So finally, we're up to evaluating and solving exponential functions. There's a couple of ways to do these, and we're going to discuss the pros and cons of them coming up here. So definitely you do want to use your calculator. That's kind of a given on this one. Exponential functions can get quite large pretty rapidly, and a lot of times they involve quite a few decimals. You can just solve them by typing into the equation, your equation right into the regular screen of your calculator and just solve that. That's great if you only need to find one value where you know the x value. You can also graph it using the Y editor. You can actually use that trace function and kind of trace and get an idea of where you're going, or use a table of values, which is probably the smartest idea, especially if you need to do more than one, or if you don't know the x value. So let's look at what I mean by that. So for this, and here's the calculator steps for this, we have f of x equals 200 times 1.04 to the x. And it says evaluate f of 14. So definitely on the last screen over here, you can see where I could just type this in. And I would have, 200 times 1.04 to the 14. And if I'm rounding this, you would say, well, that is about 346.34. So about. And 2 decimal places is pretty common for exponential models, especially since a lot of times they deal with money. If I use the Y editor, I would type in that function. So we have 200 times 1.04 to the x. On here, notice I didn't bother with the parentheses on this version. On the one in the other one, I use parentheses. You can enter it either way on either screen. This is just showing you 2 different ways to do it. When I have this, for this second option here, I went ahead and I used the table. And then I scrolled down until I had x equals 14, and it gives me 346.34, which definitely these two match. So you can see either way I can do that. And when you're just evaluating for just a single thing like f of 14, or they wanted to know like f of 6, probably that last screen would be super fast. You're just going to plug it in. However, sometimes they want something else, like determine when the function has a value of 492.94. You would have to plug a lot of those in. So instead, we're going to use that intercept method, and we want to basically graph 2. So I have that first one in there already, that y1 is the 200 times 1.04 to the x, and then I'm going to put in a second constant function of just y2 equals 492.94 to see where they cross. Now this is a huge value, 400. I mean, it's definitely not going to show up in that normal standard window. So I know that it's going to be more than 400, less than 500. So I've set my Y min and max so that that intersection will be within there. I also remember my f of 14. And so, you know, that was a similar value, a little bit smaller, but I know I need to go more than 10 for that as well. And so I've set my X max, and we'll just go for 30 on this one. And you can play with it if it doesn't work, but just to get an idea of what's going on. It was 300 some before, doubled it, made it an even number is kind of what I did to come up with that 30. And it seemed to work. As you can see, the red is that constant function, and I do see that intersection there, so it's somewhere within there, and that gives me an idea. Now, technically, to use the intersect function on the newer operating systems, you wouldn't have to have it within the viewing windows, but on older calculators and older operating systems, you have to be able to see them. So the next part, I'm just going to go to calculate. I'm going to use the intersection, which is option 5 there. Don't forget that that one is a well used. We use that on systems of equations as well. So we're going to use that intersect option 5. It's going to ask you first curve, second curve, is this close to the intersection? So basically you're going to have to push enter 3 times. Okay. And then it's going to give you the value. Now notice this value, x equals 0.22299989. Sometimes, even if it's a set integer value, it gives you a whole bunch of decimals from the algorithm a calculator uses. And actually, if I were to round this to 2 decimal places, and I would look here, it would have me rounding up for approximately x equals 23. And sure enough, when I check in a table of values, you can see y2 is always 492.94. And you can see that at 22, it's definitely under by about 1920, round in there. And when I hit 24, it's an extra 20. So 23 is our closest value there. So I confirmed it just by using a table of values. So this is question 20. This is done a similar way. You've been given a function which you could pop into the calculator right there, and it represents the value in dollars of a house t years after its purchase. So t equals 0 is when they bought it. Use this function for the statements below. So we need to understand here, we have an initial value. It's showing up here within the function. That is our a value. And so this is the value of the house when it was purchased, and that is 288 and then 3 more zeros. So 288,000. And it is growing. This is a growth because look at our right there, our b is equal to 1.07. So that tells me the value is increasing. And that rate that it is increasing is at 7%. So the value of the house is increasing at a rate of 7%. The purchase price of the house is that initial $2,800 or $288,000. For question 21, this is a similar thing. Notice this is understanding what is going on with these, but there is a definite difference on this one. We still have, this is a car, and our initial value, it was purchased at $25,300, but notice that B is 0.91. So this is decreasing. And to find out the rate at which it's decreasing, we can go 1 minus 0.91, and that's going to give me 0.09. So it is decreasing 9% each year. Okay, for question 27, we are going to want to go ahead and use our calculator because we're going to analyze the situation and then we're going to have to find the answer. And we'll use two different equations in the intersection method to do that. So first it says a house was purchased for $189,550 and it is gaining at 4% per year. If the growth rate continues, in how many years will the house be worth twice its original value? Round your answer to the nearest tenth as needed. So the first thing we want to do is analyze what we know. And we know the initial value. And we know that it is gaining at 4%, so B is going to be 1.04. So the equation to model that house, we can put that into F1, and that's going to be 189,550 times 1.04 to the x. And then we want to know when it's going to be double its value. And since the calculator is really, really smart, I can just go ahead and multiply that by 2. And it'll do that for me because why not? So I have these values in there. I'm going to put y1, y2. You are going to want to expand out that window. And since you know, like this is about 200,000, you're probably going to want to get a y max of somewhere around 400,000. So that you're going to be able to see that intersection and, you know, kind of play with the x value, find a good x value. I would probably start out a y min of 0 and then find an x min of 0 and an x max. You know, maybe start at 50 and see if you can see the intersection there. For a y min, you could just leave it as is, or you can set that equal to 0 as well. But these are just some suggestions to get a viewing window. When you do that, you should see that intersection. You're going to calculate that intersection. Remember, just click on those. So pause the video, see if you come up with the answer, and then when you do have it, go ahead and start the video back up. So the intersection is giving me a value of x equals 17.672988, and my y value is double, and it's calculated that for me at 379,100. And so you should have seen it pretty much in this viewing window. 50 probably puts that intersection towards the front end on there. But it says round to the nearest tenth. So if I look at that, and I can get my answer. So it's between 17 and 18 years, and I would say, so approximately 17.7 years. It is now doubled in value. So those are, that's the lesson here. That's the end of the slides. So do go ahead, go back through them if you need to. Otherwise, have fun with your homework, and I will see you in class.